Hello and welcome to the C++ Insights YouTube channel. I'm Andreas Fertig. I work as a C++ trainer offering classes worldwide, on-site or remote. This is my YouTube channel where I use my tool C++ Insights to teach you various topics related to C++. Welcome back to the channel. Today's episode is based on a couple of questions I got from multiple viewers like you, and this is based on a recent episode where I was talking about std move and specifically the R value qualifiers. The question that came up was basically when do we move a return value and when not, and how does this return value optimization RVO plays into this entire scenario. So this is what I'm going to answer today, and as you can see, feel free to ask questions that I answer in videos, in some upcoming videos. I'm totally open to that. It might take a while until I get to answer them, but in general, I'm happy about such comments or requests. So what I brought to you today is a specific struct or class that I often use in my training classes because it's driven like the C++ Insights videos here. We don't have a debugger necessarily. I want to get things across quick. This is the class lifeguard, and I use it to inspect object lifetimes for certain classes, for certain scenarios. So today I brought a little more than we actually need. So that one prints something out in the constructor, destructor, copy constructor, move constructor, copy sign, and move assign operator. Yet we will see the latter two we don't need, but for the complete picture and to see that I'm not, cheating somewhere or we're missing something, this is what is helpful, I guess. And the main part to answer the question, what is RVO, the return value optimization? I brought you a couple of functions. So the very first one I call RVO. So this is the actual return value optimization. So you have or you get return value optimization whenever you create the return value directly in the return statement. So more or less exactly I'm doing it here. Well, change you can do, you can omit the type here because you already specified that one in the return type in the declaration of this function. Put it back in here for better visibility. So this is RVO, and now things get a little tricky with the terminology because compilers started implementing this technology long before C++ 11 and even longer before C++ 17 came around. Up to C++ 17, this was an optional optimization your compiler could do. And most of the compilers I've seen so far, they apply this optimization. In C++ 17, you now get what's called guaranteed copy elision. And that means that in exactly this scenario, line 23, the compiler is forced to omit any copy. And for that to happen, they basically have to apply the return value optimization. So why the different wordings? Well, most likely because the standard never talks or gives advice about optimizations. This is totally up to the compilers. So we only specify how things should work, but not how compilers should be or could be able to optimize them. So this is a little bit of a way around these sort of things by saying, well, here you as a user get a guaranteed copy elision. What that means is, and this is the important thing, this is the very best you can get when returning a value, because naively, without return value optimization, without guaranteed copy elision, the compiler would create an object on the stack here in RVO and then copy that object to the return slot, so wherever this RVO ends up getting to. And this involves the copy constructor or copy assignment operator, however you do things. That means you get a copy for something that you, I, and the compiler might already know will end up at the destination and never being used locally. RVO, you can see it like the compiler is changing your code when it applies it. And instead of having an actual return, you have a void here. Now let's say we pass in by reference and call that one res obj, and we don't have a return here. Then we initialize the res obj with whatever we are creating here. Now let's use pointer, that's a little better. This is how the compiler changes this function when it applies RVO. Then a call to that, well, I should have taken the value here. The initial call looks like this. The compiler refactors the call for that one here in a way like this. So this is basically what a compiler does to give you return value optimization. And as we can see now, things look a little different here when I do it to show it to you, because we are now creating the object, moving it out. Here it is the move assignment operator. So that's not really what a compiler then is able to do or capable to do. But whenever you wonder how return value optimization looks like and how it changes your function, this is roughly the picture you can assume that is happening behind the scenes. So now that we've cleared that one, I came with a couple of more functions. One here is called RVO bad. Well, as the name of the function gives away, it's bad, so it's not even RVO, but I see a lot of people attempting to do so. So they either try to create a variable on the stack and then move it out. This is more like what we get below here. It's named return value optimization, and that's a different thing. You don't get a guarantee for that. Other things I've seen is that people construct an object and wanted to do eagerly optimize their code. They directly move it in the return statement. Now the thing is, you can see it in this RVO bad. In either case, you see more. So if I roll the code back, my apologies, that we see the actual RVO as the compiler is capable to do it. The original code the compiler generated me for this first call to RVO is simply a constructor and destructor call. All right, nothing more. If we look at RVO bad, which is the second call here, then we can see, oh yeah, it's a constructor call, it's a move constructor, and since two objects now got constructed, we have two destructor calls. Maybe the two destructor calls aren't that expensive, but they're functions calls after all, and we see them appear here. This is the version, and the other version I showed you is that people try to make that value up in the return slot. This looks closely to RVO, but we still see that the output here is more than in the actual RVO case. The reason for that is that you only get return value optimization if you construct the object and return it like in line 23. Once you start changing the object, applying functions to it, like I do here on line 28, even if it's in very good faith moving that thing, the compiler says hands off, I'm not optimizing this function, because it can no longer be 100% sure that what we constructed here is actually what ends up at the destination and doesn't get modified, changed, or whatever in between. So this is the very important distinction. You really need to write your code like in line 23. No step move here. Despite the idea that you are very efficient and the move constructor gets called in all fairness, it's more operations in the RVO bad case than in the RVO case. And this is why I, a long time ago, wrote a blog post that basically says don't move a return value ever. Well, with an exception maybe or two. We are getting to that. So the initial code I had here was more like the NRVO. And the N here stands for named return value optimization. And this is whenever you prepare an object and return it later. So this is still a case where the compiler can say, yeah, I can apply return value optimization here and skip the copying and creation. So this is what we see here. So this named return value optimization in my case yields the same code as for the first one. All of you preferred the second style, might be a little bit relaxed, you still get good code generation. But from a standards perspective, and with that from a compiler's perspective, The only thing that is guaranteed by the standard is guaranteed copy deletion for this RVO case. So for the simple RVO, not the named return value optimization. While Clang here does this even for O0, so there's no change between O0 and O3, you don't have the guarantee from the standard. So that code could lead to a couple of copies or moves, whatever. And now there's the other thing. Once you start using named return value optimization, you might end up writing code like this. So you have the two lifeguard objects A and B. Based on an input parameter to this NRVO bad, you decide which of the two objects you're going to return. Imagine it might be real code where the two objects are really different by constructor parameters or whatever. This is a case, we can see this down here, where the compiler generates you copy construction and a lot of temporary intermediate objects, because we have two here, so they to get destroyed. This is when the optimization nearly always stops. It depends on the compilers, their optimizers, and how complex of code they wanted to decipher and prove that it's always that one object or something like that, so they can apply return value optimization. But in general, assume once you start using that object or having different return path, you lose named return value optimization. I mean, we can see, right, 2 lines compared to way more than 2 lines. So if you want efficient and fast code, go the return value optimization path. The last function I have is this non-copy, non-movable RVO. So my lifeguard object, let's simply say we take the others out here, because we're now going to modify the lifeguard object itself, and say here we have our copy constructor. We say that one is deleted, and we say that our lifeguard move constructor is deleted as well, and so are the assignment operations for copy and move. So now what I've created is basically a non-copyable and non-movable object, so even tighter than a unique pointer. And the purpose now of return value optimization is I can still return that object using return value optimization. So I should put the lifeguard on here. And this is the other side of the powers of return value optimization, that we now can create types that are neither copy nor movable, but we can still return them from, for example, a factory function and just use it in place. So this is the thing that I think is also important. It's not just that you get very good code generation with return value optimization, you also can approach a couple of use cases that otherwise would be very difficult to do. And while compilers could do that all the time, they were forced by earlier standards. So in C++14, this code would not compile, because despite that compilers already had implemented that optimization, it was just an optimization, and the standard said they can only do that if the object is actually copyable or movable, which it isn't. So they are disallowed to apply this optimization by other rules of the standard. And once I go up to C++17, we can see this code compiles. So now we discussed that. Let's say the remaining question is, what is the exception for the never move a return value? I have one here prepared for you.
Like this content? Your company can hire me to teach a C++ class with even more details answering your questions. Feel free to reach out.
This is from the recent episode. We have this class book. It stores a std string, constructs from a std string, shows the destructor. It's not very important today. And then we have the single function read. I'm going to read a book, right? And I modified it now in the spirit of being really efficient. So it's a really bad idea, but what if read would say std move on m contents? Aside from it leaving the string in a rather undefined state, the m contents, it would not force return value optimization. So this is a place where this doesn't win. On the other hand, this here also doesn't give you return value optimization because the object here already exists in the class. So the compiler cannot apply the trick and say, well, we feed the actual return object in as a pointer because this is a class member. So you don't get return value optimization there. But the place where you can move and where you potentially should move is if you use the R-value qualifier to say, well, this here is for the L-value case, and this here is for the R-value case. So in the R-value case, you have special knowledge. You now know that this is used with a temporary object, so it will expire soon anyways. This is when you can say, now that I have that knowledge and I can teach it to the compiler, this is when I can move this value, this return value, because you don't get return value optimization in any case. And here you know that after that call, your object will get destroyed. So instead of paying for the copy, this is the only place in the code where I would say, yeah, you can std move here, you should std move here if you want to get efficient code or fast code. All right, I hope that cleared things up. And well, should you have more questions around this topic, as I said, reach out and I will record another episode.
That's it for today. Thanks for watching.